Okay, what we're going to be doing today is learning how to construct a cross-section using the kink method. So what we have here is our map. We've got 5 sites on it. 2 of them are in shale and 3 of them are in sandstone. And we have strike and dips at each of these sites. So what we want to do is be able to build a cross-section with this map. And using these data in the stereo net, we've determined that the trend and plunge of the fold is going at 40 degrees, which is this line here, and it's dipping or plunging 30 degrees. So this full data is going to be really important for being able to project our data up onto our cross-section, which is here, A to A prime. Now the first step is to get these structural measurements onto our cross-section. So what we want to do is draw a line in the same direction of the plunge. So we'll just keep our line that's here as parallel to the plunge of the fold and draw them onto our cross-section. So I'm just going to put little tick marks on the cross-section where these structures end up falling. And I'm doing the center of the structural measurement because that's like exactly where it was taken. And because our fold is plunging, where these end up projecting onto our cross-section are actually not going to be right on the line. They're going to be either above or below the line. So what we also need to do is measure the distance from the point along the direction of trend onto the line. So. All right, so we've measured the distances onto the cross-section. Now the next step is to determine where the points plot on the cross-section, and we're going to use trigonometry for that. And the plunge is 30 degrees, so we do 30. Take the tan of that, and tan is equal, tan theta, or tan of the angle of the plunge is equal to adjacent over opposite, so it's equal to opposite over adjacent, so it is equal to the height above or below the cross section over the distance to the cross section. So another way to say that is tan theta, or in our case tan 30 degrees, times the distance to the cross-section, so the measurements that we just made, is equal to the height above or below that cross-section. And just for example, tan theta is about 0.577 times, in this case, the sandstone, which is 7.3, is equal to is equal to 42.1 millimeters or 4.2 centimeters. So that's, and because we're on the kind of down plunge side of the cross section, that means we're projecting up, because what we're essentially doing is projecting this bed all the way to where it originally would have been kind of on the cross section. And because this is in the direction of plunge, we have to project up, which puts it actually into space. So kind of where this bed was is now eroded away. Whereas in this in S2 here, the sample will be projecting down. So the next step now, we would calculate all those measurements, and you'll have the height above or below, kind of a list of those for S1, 2, 3, 4, and 5. And now we start actually constructing our cross section. We'll take a blank piece of paper, fold it is easiest, and to transfer on, so we put our A and A prime, mark a little tick for each of that, and then we mark a tick for each place that our cross section, or where our structural measurement projected onto our cross section. All right, so now we've got A and A prime, and just make sure that we write down which of these structural measurements they are so we don't get confused later. S2, S2, S1, S4, and S5. All right. So we've got our roughed out cross section here. I'll just secure it for camera so it doesn't get too shifted out in your shot there. And we'll draw a line. So if we had topography on our map, this is where we would start. We would also indicate where our contour lines were, so we'd sort of have a cross section showing the hills and such. But just to simplify things for this example, we're not having any topography, so just imagine we're on the Great Plains and it's just completely flat. All right, so the next step now is to use the calculated above or below measurements. So the one that we did was S4. We calculated it was 42.1 millimeters above. So we measure 41 and just a little bit millimeters, and we draw a point here. So this is where that bed projects up plunge onto our cross section. And we do similar things for all the other ones. So S1 was this one here, and it is 10.4 millimeters above the cross section, so here. And S3 was 15 millimeters above. S3 is this one here, so 15 millimeters above. And then S2 is 16.2 millimeters below. Now it was on the other side of the cross section, so it's got to be below. So it's actually projecting down to hit the cross section. And then S5 again was above, and it is 27.1 millimeter above. So these are where the individual beds that are defined by those structural measurements are projecting up plunge of the fold, or in this case down plunge of the fold, onto our cross sections. So if we were looking at a big volume of rock before there was ever any erosion in this area, if we just followed that bed along, this is where it would hit our cross section. Now the next step is to put the actual dip measurements onto our cross section. Now what this is though is we need to do the apparent dips. Because the cross section isn't perpendicular to our bed, it's not just the maximum dip. That you would get the maximum dip is equal to the apparent dip when the cross section intersects the bed at 90 degrees, so if it's perpendicular to the bed. But because not all these measurements have the stripe perpendicular to the cross section, we need to use apparent dip. And you can do that with trigonometry, but it's probably easiest just to use apparent dip tables. This is an apparent dip table, and what you have is the angle between the strike and the direction of the cross section, and then the true dip down here. Now these are in increments of 5, so you just have to be, you have to approximate a little bit. So if I just take one of these, we'll do S1. So S1 has a true dip. S1 has a true dip of 32 degrees. So we're going to go true dip, it's 32, so it's going to be in the middle between 30 and 35. And then we can go to the angle between the strike of the section and so I've got another map here, so we're just going to measure the angle between the strike and the section. So if I just draw my line parallel to strike onto our cross section, and have a nice long line there just so it's a little bit easier to read off. Use your protractor and we can count up. So it's 10, 20, 30, 33 degrees. So the intersection of the cross section and the strike is 33, which is down here, and if we draw the line between the two, it's where they intersect. It's more or less where our apparent dip is. So we're kind of in between 22 and 18, and in between 19 and 16. So something like 19 degrees is our apparent dip. So for S1 here, I just put in brackets usually the apparent dip, which is 19 degrees, and then we measure it onto our section. So put the center of our protractor at that spot and count down 19. So 10, 15, 16, 17, 18, 19. And then we sketch that in, just a short little line of the apparent dip is there. And then we'll do the same for each of the points. So if I go next to S2, its apparent dip is 56. So it had a true dip of 57, and since it's both a steep dip and also relatively close to the perpendicular to the section, it has much less variation than we had with S1, and its apparent dip is 56. So again, we'll put our protractor down, 10, 20, 30, 40, 56, and we'll draw a little bit of a line there. It's probably a good idea to start kind of cleaning up these little tick marks that we have with our eraser, because it can get confusing if you get too many little dots on there. And now we'll go to S3. That's an apparent dip of 60. 10, 20, 30, 40, 50, 60. There we go. And now S4 is 33. 10, 20, 30, 3. Oops, forgot to put these. 33. S2 is 56 and 60. And then our last one is 5, which is 39. 10, 20, 30, and 9. Okay. And now we've got our data projected onto our cross section, and we've got the apparent dips. So this is, if we took a slice of rock through the section, right where this cross section is, this is kind of how the beds would look if we spray painted the beds from each of these measurements. Okay, so we've got our cross-section with our apparent dips marked in for all our projected data. The next step now is really where we start doing the kink method. What we've been doing up until now is things that you'll do for most cross-sections, but the kink method really begins at this step where we need to bisect our angles of our different strike and dip. So the first step on this is to measure in between each of the adjacent points. So this one, 42 millimeters, so at 21 millimeters we put a check, and we do that for each of the data points. And now what we need to do is to bisect the angles. The way we do this is we take an average of the different measurements. So just because it fits better on the page, we're going to do S1 and S2 here. And the apparent dips of S1 is 19 and S2 is 56. So what we do is we average this. So it is 19 plus 56 divided by 2, so it is 37.5 degrees. Now what this is measured kind of over from vertical. So put the center of a protractor on that point that we measured between those 2 points, and then count over 10, 20, 30, 7.5. And then we'll draw a line between them. And we do similar things for each of these. So the next one we're going to do is between S2 and S3. So this is 56 plus 60 divided by 2 is 58. We go 10, 20, 30, 40, 58. And then the next one's a little bit tricky between S1 and S4, where we have where we have to keep the sign in mind. So we're at apparent dip of 19 here, and this is an apparent dip. So we're going in the wrong direction there. When I plotted these on the first time, there was a slight error there that we have to make sure that we're keeping in the correct dip direction each time. So it's not just the angle, but also the direction. So these two should be dipping this way. Now, the next step, so we're bisecting between 19 and 33. But we have to remember that this is dipping the opposite direction. So if we're calling this direction of dipping positive, then this one will be negative. So we're 19 minus 33 instead of plus, and divided by 2. So we have minus 7. So this line dipping this way was plus. So if it's dipping this way, then it's minus. So we'll go minus 7. There we go. And then the final one is minus 33 minus 39 by 2 is minus 36. So that's in between these ones here. We'll go up and 10, 20, 30, and 6. And again, we'll draw our line through there. So basically what this has done is it's split our section into different domains of different dips. And these are the domains that are defined by our different strike and dip measurements. So you'll have more data points, so you may have a few more domains. If you have ones that are very similar, there's probably not a point in splitting them into different domains because it's not going to change anything that much. But each one of these is a big enough difference. Maybe these ones we could have called the same thing and just done an average. But now what we do is we pick a line. So what we're going to do here is use the measurement taken at S2, and this is because this is a shale, and it's like the uppermost in section shale that we have, because our other shale is over here at S3, and you can kind of see it's down from S6. So we're going to trace around between the lines, and then as soon as we hit the next line, we go in the direction of the apparent dip of the bed in that domain. So we're here. So I'm looking through my protractor here and making it parallel to that. We can also measure it down here. Both is fine. We're just paralleling it, and then we're into this domain. So now we use the apparent dip from S4. And then here, now we're in the domain defined by S5, and we go parallel to that. So it's just a little bit steeper of an angle than what we had before. So what we've done is we've projected all the beds onto the section, and because these are our measurements, these are defining all of the bedding parent dip direction within the domain. So it's like the average. So because we picked the equal distance in between these 2 points and drew the line that bisects that changes our domain. Now as we add more and more data, kind of these segments are going to be smaller, and this is going to be less kinky and more smooth. And if you have an infinite number of structural measurements, it should define like a perfectly smooth, accurate fold. Now the one thing, because we don't actually have a contact, if we had a contact, we could draw that along, and then that would be our contact. But we don't have a contact. We know that these three, S1, S4, and S5 are sandstones, and these two, S2 and S3, are siltstones. So the contact has to be in between those. So we've drawn a line that went through the projected point for S2. We know that that's a siltstone, so this here is all siltstone. Now we want to go kind of the first sample up stratigraphy to be our to be the sandstone. So I think it's probably this one here, which is S5. So what we'll do is we'll do the same thing here. So in this domain, we're parallel to S5. In this domain here, we're going to go parallel to S4. In this domain here, we're going to go parallel to S1. And in this domain here, we're going to go parallel to S2. And we're completely above the section line now, so this is all in sky, so we're not going to worry too much about S3 for this part. Now, the next step, so what we know here is that this is sandstone, this line here is sandstone, and this line here is siltstone. So the contact is somewhere in between those. Had this projected line actually been down there that we knew was sandstone, we'd actually have to do it again there and just put it around, but it's above, so we picked the right one to be the kind of lowest stratigraphy sandstone and the right one to be the highest stratigraphy siltstone. So the contact is somewhere in the middle there, unless we don't have any other data, so we're just going to do the average. So this is 6.2, so 3.1. So this is equal distance in between these two, the siltstone and the sandstone layer. So we're going to call this the contact. And because we're not that sure of it, we're going to dash the contact. And it'll be our approximate contact. So we know it's somewhere in between those, but we're not exactly sure where. Let me just do the same thing. So this is the approximate contact. Now to complete the cross-section, what we would do is actually erase all of these construction lines and color this in probably yellow for sandstone and this probably brown for siltstone. However, for your assignment, I want you to leave these lines here so I can see that you've done it correctly, and if you've made an error, I can determine where you made that error and how to give you part marks. But I would like it colored in, so that you don't have to color anything above here because that's all just sky. This would all be yellow, and then this would all be brown. And that's how you do a cross-section by the kink method. Now, the reason why we do the kink method is because everything is based on data. So there's not really much artistic license used in this. This is all 100% based on the data. And any deviation is just because our data set isn't completed enough. So we're not putting any bias that is unrepeatable into it. Whereas if we're doing our own interpretation, even though it might in the end approximate the fold a little bit better, it is an interpretation and it's less repeatable. And if we had more data, this would be a lot more smoother of a fold, like that would kind of be a little bit more what you would actually see probably in the outcrop. Yeah, but that's the kink method, and it's like I said, it's a nice way to do a cross-section that shows the stratigraphy because it is 100% utilizing data instead of being subjective estimates.